The fastest thing we've ever seen. Superatomic Semiconductor sets a speed record. Semiconductors, particularly silicon, are fundamental to the operation of various electronic devices such as computers, cell phones, and the device you're currently using. Despite their widespread use, semiconductors have inherent constraints. The atomic structure of these materials is subject to vibrations, resulting in the generation of quantum particles known as phonons. These phonons lead to scattering of the particles, either electrons or electron-hole pairs termed excitons, responsible for transporting energy and information in electronic devices. The scattering occurs over extremely small distances, nanometers, and brief time spans, femtoseconds, causing energy dissipation as heat and imposing a limit on the speed of information transfer. The fastest and most efficient semiconductor yet, a superatomic material called Re6-octa-selenium dichloride. Rather than scattering when they come into contact with phonons, excitons in Re6-octa-selenium dichloride actually bind with phonons to create new quasi-particles called acoustic exciton polarons. Although polarons are found in many materials, those in Re6-octa-selenium dichloride have a special property. They are capable of ballistic, or scatter-free, flow. This ballistic behavior could mean faster and more efficient devices one day. In experiments run by the team, acoustic exciton polarons in Re6-octa-selenium dichloride moved fast, twice as fast as electrons in silicon, and crossed several microns of the sample in less than a nanosecond. Given that polarons can last for about 11 nanoseconds, the team thinks the exciton polarons could cover more than 25 micrometers at a time. And because these quasi-particles are controlled by light rather than an electrical current and gating, processing speeds in theoretical devices have the potential to reach femtoseconds, 6 orders of magnitude faster than the nanoseconds achievable in current gigahertz electronics. All at room temperature. In terms of energy transport, Re6-octa-selenium dichloride is the best semiconductor that we know of, at least so far, Delors said. A quantum version of the tortoise and the hare. Re6-octa-selenium dichloride is a superatomic semiconductor created in the lab of collaborator Xavier Roy. Superatoms are clusters of atoms bound together that behave like one big atom, but with different properties than the elements used to build them. Synthesizing superatoms is a specialty of the Roy Lab, and they are a main focus of Columbia's NSF-funded Material Research Science and Engineering Center on Precision-Assembled Quantum Materials. Delors is interested in controlling and manipulating the transport of energy through superatoms and other unique materials developed at Columbia. To do this, the team builds super-resolution imaging tools that can capture particles moving at ultrasmall, ultra-fast scales. When Tullyig first brought Re6-octa-selenium dichloride into the lab, it wasn't to search for a new and improved semiconductor. It was to test the resolution of the lab's microscopes with a material that, in principle, shouldn't have conducted much of anything. It was the opposite of what we expected, said Delors. Instead of the slow movement we expected, we saw the fastest thing we've ever seen.